So where we left off last day, just a really quick review. I said for horizontal circles, I find a top view picture sometimes isn't that helpful. The only time it might be helpful is if the question is frictionless, which means I'm probably going to ignore gravity. I don't know. I tend to draw a front view picture. You saw my amazing drawing of all sorts of little cars and things like that. We talked about how you could create artificial gravity with a space station. And we paused at the Gravitron. I think I'd confess to you my shame. I've never been on this ride. Like to be, but I haven't been on it yet. The Gravitron. Where do I have it, Mr. Dewick? Got to pause the video for a second while I go hunt for it. So the Gravitron is a ride. It spins its riders around in a circle, and then usually the floor drops away. If the ride has a radius of 4.8 meters and it rotates every 2.5 seconds, what's the minimum coefficient of friction required between the riders and the wall of the circle? Huh? What's this question want me to find? What's mu? I don't know. What's mu with you? So, okay. Any suggestions on how I might want to start? You know what this is a job for? Free body diagram. I'm going to look at this person here, and I'm going to label the forces acting on him or her. What are the forces acting on this person? Get the obvious one. Okay. Is this person sliding down the wall? Is this person sliding up the wall? So there has to be an equal force up. What force is that? You know, I'm not sure yet, so I'm not going to guess yet. I'm going to move on and see if I can reason my way there. What else? Sorry? Which way? Okay. There has to be, first of all, I would say, what path is this person tracing out, Connor? So there has to be a force pointing inwards. This is Fc later on in my equation, but I'm not going to put it on my free body diagram. You said this is a normal force because, oh yeah, I guess it's the wall pushing them sideways. It's a surface pushing them sideways. Does that help you figure out what the upwards pointing force is? Max, what? It's friction. It's friction. This ride wouldn't work very well if you were laying on ice, if you were leaning against an icy wall. This wouldn't work very well. Okay. It wants me to find the minimum coefficient of friction. I guess here I have two equations. Vertically, I have this. Friction equals mg, and those are in balance because you're not sliding up or down. Is that okay, Robbie? You okay with that? Horizontally, I have normal force equals what's pushing me in a circle. Okay. What's this question want me to find? So let's start with, I guess, this guy. It didn't say friction, it said coefficient of friction. But let's start with that guy. Okay. So if I take this equation, I would say friction equals what times what? So I'm going to go mu times the normal force. That equals mg. I don't know the normal force. Now I can't say, oh, but look. I know another force the same. Wait a minute. Oh, but look. I know another force the same size as the normal force. It didn't even appear on my free body diagram, but what force is the same size as my normal force? Fc. So I can now say this. Mu Fc equals mg. Okay. What's Fc? Well, that's going to be mu MAC equals mg. Because centripetal force is always ma, but you're moving in a circle. So we're going to use either the v squared over r or the 4 pi squared r over Well, which one am I going to use for this question? It all depends on what they gave me or asked for in the question. Which one, Robbie? Did they give me the period in the question? There it is. That's the period. That's time. That's T. So I'm going to say, oh, by the way, can little kids and grown-ups go on this ride together? Cool. So I'm going to get mu 4 pi squared r over t squared equals g. What do they want me to find here, Duncan? So I can get the mu by itself. By the way, in real life, probably you would know the coefficient of friction. You would know how sticky the fabric against which people were leaning, and you could calculate t, how fast, how long you need it to take to rotate for the ride to work, and you build in a safety margin, have it go a little bit faster. But you don't want to go too fast, because if it goes too fast, they're going to feel so much inertia that it's not going to be an enjoyable ride. They'll have trouble breathing. Don't want to go too fast. So to get the mu by itself, I guess mu is going to be gt squared all over 4 pi squared r. G, 9.8. T, did I say 2.5? Yeah. All over 4 pi squared. What's the radius of this ride? 4.8 meters? Double check, did I type that right? Did you get 0.3232? 0.323? Units for coefficient of friction? None, right? I wrote here, show gravitron picture. So there's the gravitron picture, riding the gravitron like a boss. So in horizontal circles, generally, our vertical forces are balanced. You're not sinking into the ground like quicksand or flying into the air like Superman. The net force inwards is always ma, and I'm going to put a little c there, which can be mv squared over r, or it can be m4 pi squared r over t squared. Horizontally, we're not going to have you be speeding up or slowing down. You're going to be going at a constant speed. So the tangent forces are going to be balanced. Okay. A couple more examples here. The picture below, turn the page, shows a frictionless table in top view. The mass is 4.15 kilograms and it's attached to a 2-meter long string. And the mass is moving at 2.5 meters per second. So I guess it's spinning, and the table's made of ice, so the mass is spinning around at a constant speed. It says write force equations and then solve for the string tension. Okay. What are the forces acting on this mass? Get the obvious one. Sorry? Okay, so if we did a front view, there's my axis of rotation. Here's the mass, here's the string, and it's going around, I don't care which way, this way. You're telling me we would have gravity down. Is it sinking into the ground like quicksand? Is it flying into the air like Superman? Normal force up. And it is moving in a circle, so there does have to be a force pointing that way. What's pulling it in a circle? So when a car was going around a corner, we said friction. What's causing this to move in a circle? Tension. Okay. For my force equations, I think in the vertical direction, everything is balanced. Horizontally, who's winning? Who's losing? going to be MAC. Tension is going to be M. Which version of circular acceleration am I going to use? The 4 pi squared r over t squared or the v squared over r? Oh, did they give me the speed in the question this time? So what was the mass? 4.15. And the speed is 2.5 squared. And the radius was 2. You get, I guess, 13.0 if I round off properly. Did I type that in right? I think so. Is that right? By the way, what if I went twice as fast? What happens to the tension? It's 4 times bigger. Okay. This is why it's easier to snap a rope if you're, well, swinging it in a circle horizontally, but more specifically, swinging at the bottom. If you're swinging it vertically, like a rope swing, the rope swing can snap on the bottom, and a slight increase in speed doesn't lead to a slight increase in tension. It leads to the square of the increase in speed and tension, which is why ropes can snap so easily. Let's combine this. So, we have a 0.009 kilogram ball, this little thing here, and it's attached to a larger mass, 3.6 times 10 to the negative 2, by a string which passes through a hole in a frictionless surface. Let me just pause the video and help you visualize what's going on here. James, what does this question want me to find? Which I think means eventually when I do my circle equation, I'm probably going to use the v squared over r and not the 4 pi squared r over t squared. Yes? All right. There's going to be a couple of free body diagrams here because there's 2 masses. This is sort of like a glorified Atwood machine, except now we've added moving in a circle as well. Let's look at the forces on this bottom mass here. James, my friend, what are the forces acting on big M? Get the obvious one. I'm going to call that big mg. What else? There's a rope. Yep. Those are the forces acting on big mg. What are the forces acting on little m, the ball? Folks, get the obvious one. Okay, we have gravity down. Little mg, I'll call that. Is it sinking into the table like quicksand? Is it flying into like Superman? We have a normal force up. What else? Tension. James, what did you say this question want me to find? Of? Okay, let's write an equation for the ball. For the ball, vertically everything's balanced. What would your equation be for the ball horizontally? Tension equals what's pulling me in a circle. Tension is going to be little m, and then James, you told us to use the v squared over r because it wants us to find the speed. Quick check, do I know little m? Yeah, 0.009. Do I know R? 0.42. Do I know, oh, it wants me to find V. Do I know the tension? Ooh. Or do I? Pardon me? Ah, from this right here, I know that tension equals big mg because that's also balanced. That's also balanced. So, we can plug that in. We'll get big mg equals little m v squared over r. Now this time the masses don't cancel because those are very different masses. But now I can get the v by itself. I think we're going to times by r divide by little m, square root. I think the speed is going to be big mg times r divided by little m square root. It's going to be square root of big M is 0.036, 3.6 times 10 to the negative 2, 9.8, 0.42 divided by 0.009. And I get, do you get 4.06? Am I wrong? I'm good? Units, it's speed. Meters per second. Horizontal circles. Put your pencils down. So what's your homework? I already assigned number 1 last day. I said you didn't know how to do it. Hopefully now you're okay with it. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 12 again for some reason. You can scratch out 13. I had to cut corners. No pun intended. Yes, pun totally intended. And 14, although banked corners are cool. 16 is fair game as well.